Welcome to this lecture number 33, and in this particular lecture we will talk about saltwater intrusion in aquifers, and topics to be covered is uh, analytical solution of saltwater intrusion in coastal aquifer, and we will continue from the previous lecture class, and we will also talk about density dependent flow, density dependent saltwater intrusion models. So, this is our lecture number 33, and in this one we will talk about saline water intrusion in aquifers, and topics to be covered are: first one is analytical solution of saline water intrusion in coastal aquifer. Will continue from previous lecture class, and next one is density dependent salt water intrusion model. We have already talked about saltwater intrusion in confined and unconfined aquifers. Now, let us derive the relationship that exists in oceanic islands. So, interface in an oceanic island. So, in this one, let us say we have an oceanic island which is surrounded by ocean from all the sides, and the interface is like this, and we have groundwater table which is also symmetric in nature. This is central line, and we have infiltration or precipitation from the top of the oceanic island, and this rate is n, and let us consider this is having equal radius with r. For a arbitrary location we have this distance below the ocean level is denoted as psi r, because this is radially varying for oceanic islands, and this is at a distance r from center, and our freshwater head H f, which is again a function of r, because this is again varying radially. So, this is our groundwater table, and this is location of interface, and this is location of fresh water, and we have salt water in this position. So, in this case, if we write our mass balance equation, so we can write our basic equation and this basic equation shows that the QF radially, that should be equated with the recharge or infiltration or precipitation from the top of the island as this equation. This is varying with the radial direction, where we have this QF or our flux is 2 pi r into Kf. Kf is the freshwater hydraulic conductivity, Hf plus xi dHf and dr. So, in this case also we will utilize our Guyben-Herzberg approximation . So, with Guyben-Herzberg approximation, we have Hf equals to xi by delta, and delta is our rho f by rho s minus rho f. So, with this approximation, we can write it as our dQf by dr is equals to, we have 2 pi r n, and from this one we can write this Qf as we have pi n r square plus C1, where we have integration constant now. For oceanic island, we can specify certain conditions. So, number one condition for oceanic island, we can specify that at r equals to 0, we have Qf equals to 0. So, it implies that we have C1 equals to 0. So, thus we can write our equation as QF equals to pi n r square, and we can again replace our QF from our previous relationship as 2 pi r kf hf plus xi dhf dr equals to pi n r square. Or if we replace this hf with our Geibel-Herzberg approximation, then we can write it as 2 pi r kf, and this as xi by delta plus xi, and this one again xi by delta r square. Or we can write it as minus pi cancels from both the sides. We have r and we can write it as d xi by dr 2 xi equals to n delta square by kf into 1 plus delta. Into r. So, with this thing, delta square and n r we have. So, with this thing we can write it as minus d psi square dr equals to so this is equals to we have this n delta square kf 1 plus delta r, or if we simplify this and just exchanging the sign both the sides, psi square with integration we can write it as n delta square kf 1 plus delta and r square by 2 plus C2. Again we have another integration constant. So, another assumption we have for this particular thing is that if r equals to capital R, then we have xi value is equals to 0. So, at the end of the oceanic island we have the xi value 0. So, with this let us say write this as 33.1, and next one we can just write it as 0 minus n delta square kf 1 plus delta and this is capital R square plus C2, and we can write it as 33.2. So, if we subtract this equation 33.2 from 33.1, then we can directly write it as I square equals to minus n delta square kf 1 delta r square plus this is n delta square 2 kf 1 plus delta r square, or finally we can write it as n delta square 2 kf 1 plus delta r square minus r square. So, this shows the relationship between the location of interface, the recharge rate, and different radiuses. This is radius of island, this is hydraulic conductivity, and interestingly in this case, if we have n, which is our recharge rate, if n equals to 0, then the xi value is always 0. That means, if there is no recharge in oceanic islands, so it means there will be intrusion from the bottom. So, next thing we will discuss another important solution in case of our saltwater intrusion problem, that is again sharp interface approximation of the problem. So, in this case this is popularly known as Strack's solution. In Strack's solution, we consider two different zones for modeling our saltwater intrusion problem. In our three consecutive derivations, that is for confined, unconfined aquifers and our oceanic islands, we have talked about single zone modeling, but in case of Strack's solution, we consider a two zone model for problem solving in saltwater intrusion modeling. So, we have location of sea surface or ocean surface, we have interface located as toe or T, and we have groundwater table, so in this one the problem is divided based on the location of toe. So, from the left hand side we denote this particular zone as zone 1, and right hand side we denote it as zone 2. So, in this zone 1 and zone 2, we have two different situations. Zone 2 consists of only fresh water aquifer, and in zone 1 we have both salt water and fresh water thing that exists with a sharp interface. So, Strack, what it did, it defined certain potential for defining different piezometric heads. So, we can simplify or we can write it directly according to our previous modeling conventions. This is our HF, this is xi, and q prime that is entering from zone 1 to zone 2, and we have thickness of this phreatic aquifer below sea level or ocean level is B, and this is our seawater position, this is our freshwater location, and this is impervious bottom with, in Strack's solution, the coordinate system is taken from left to right, and it starts at the beginning of the interface. So, in this case we can say that the Strack, that is, he derived this particular formulation in 1976, developed a model that describes the freshwater flow in both zones using a harmonic potential as the single variable of state for both zones or both zones. So, what is this Strack solution? In common boundary, it requires that, so on the common boundary in each zone we require the continuity of both the piezometric head and the flux. So, at the interface level, we require that continuity of both piezometric head and flux. So, using this thing, two things can be defined for both zone 1 and zone 2. So, for zone 1, we have phreatic flow above interface. So, in this case, Strack's potential phi is defined as equals to HF plus xi into HF. If we utilize our things, so we can see that this is basically our half, this is again we have this for Geibin-Erzberg principle for phreatic aquifer, we have xi equals to delta into HF. So, in this case, for in case of HF, we can replace it with delta HF plus delta HF plus HF into HF. So, we have half 1 plus delta HF square, and for flux continuity we have q prime. So, which is in vector form k HF plus xi, this is HF and k del xi del phi, and this thing is basically freshwater discharge per unit aquifer width. In case of zone 2, which is fresh water only, we can define our the Strack's potential as phi HF plus B square 1 minus delta by delta B square, and again we can define our flux thing as q prime equals to minus k, this is HF plus B prime HF minus k phi. So, at location T, or at toe location we have B, which is equals to HF into delta as per our continuity of zone 1 and zone 2, and by using Geibel-Herzberg approximation. So, in this case we have phi which is equals to phi tau, and we can directly write it as B square by 2 delta square. So, if you utilize this equation or this particular equation, we will get same result, because this is at the transition of zone 1 and zone 2. So, using this thing or continuity of the flow is considered, and for steady state flow, steady state flow condition, we have dot q prime in each zone So, from this one we can directly write the Laplace equation for this particular case. So, this means that phi is harmonic function in the respective zones. So, it satisfies our Laplace equation. So, Strack utilized this particular approximation and theory for derivation of coastal aquifer modeling with single pumping well, and he showed that phi can be constructed as phi equals to q naught prime x plus w 4 pi k ln x minus x w, which is location of x w is the location of pumping well and this is can be utilized for modeling of pumping wells in coastal aquifers with simple approximation. Again, this phi can be replaced with phi tau, and which is equals to 1 delta p square delta square equals to x 2 delta square, where q w we have is equals to pumping rate from the aquifer with pumping well, q naught x prime, this is the flow that is occurring, horizontal flow that is occurring from coastal aquifer phase zone towards sea. So, if we write this thing, we have one top view, this is basically top view in top view we can see that this is y axis, this is x axis, and this is the location of pumping well. So, with this location of the pumping well, this is x w. For different pumping values, we can have different location for this is different location for toe, this is ocean, and this side we have this flow, horizontal flow that is coming from freshwater aquifer towards sea, ocean, q naught x, this is prime, and this is this thing is basically k by x. So, as it is in our previous thing. So, initially if we have this q w equals to 0, the location may be like this. However, if we have higher pumping values, so the location of interface that will change, and that will be symmetric with this x axis. And finally, it has been observed that for a specific value it shows a critical pumping location, which will signify the end of no flow zone. This is the influence zone for pumping, and at this point it shows 0 flux situation, and it is called as QC or critical pumping. So, next thing we will discuss is this density dependent flow models. What is this density dependent? Density dependent salt water intrusion model. So, in this model, a transition zone is considered instead of a sharp interface that is used for our sharp interface modeling using Gaussian-Herzberg principle. Let us say we have some semi-pervious uh, semi-pervious location, and we have another this is again impervious bed or impervious bottom. This is the location of transition zone. So, in transition zone, it is considered that the density is in between fresh water and salt water. And during this kind of modeling, we need to consider the composition of seawater, because the composition of seawater is important for exact modeling of using its exact modeling of saltwater intrusion using density dependent flow models. So, in this case, this density is considered to be a function of pressure, temperature and salinity. So, this density is a function of pressure, temperature and salinity. So, if we see the variation of density with this is density of water in kg per meter cube, this is temperature is 0, 5, 10, 15, 5, 10, 15 and degree Celsius. So, this is with a difference of 1 kg per meter cube. This is 1014, 1015, like that. We have so with this thing, it has been observed that this density varies like this red line, where we have a chloride concentration of is considered to be 1.2% of chloride. Next, if we increase this, we decrease this chloride percentage, 1.1% of chloride, and again this is 15, say in between also there will be different curves. So, we can see that there is some kind of nonlinear relationship between density, this is temperature, and this chloride, which signifies the salinity for salt water. So, depending on the chloride concentration, depending on this chloride concentration, type of groundwater we can define. So, classification of groundwater on the basis of chloride concentration. So, type of groundwater, and milligram chloride per liter. First category is oligohalline. We have the range 0 to 5. Oligohalline fresh, we have 5 to 30, then fresh we have 3 to 150, 30 to 150, fresh brackish, that is 150 to 300. Then we have brackish, which is 300 to 1000. Then brackish saline, you have 1000 to 10,000. Then saline, we have this range 10,000 to 20,000, and the final range is hypersaline or brine. This is greater than 20,000. So, this is the classification of groundwater on the basis of chloride concentration. So, different geochemical composition is required for modeling of detailed modeling of salt water. Geochemical components. Seawater has a uniform chemistry due to the long residence time. Of the major constituents. So, for this one, to know something about salinity, chloride is important thing. So, time series of steadily increasing chloride concentration can indicate the early evaluation of salinity breakthrough from seawater, can indicate the early evolution of salinity breakthrough from seawater. So, there are other components or other indicators exist that can be used for identification and evaluation of salinity level. So, we will discuss those topics in the next lecture class. Thank you.